Hello everyone. In this tutorial, we are going to solve some of the linear algebra questions that are asked in the GATE exam in the previous year. So let's start. Question number 1 says, consider the matrix. Okay, we have given here J6 matrix, which is 6 cross 6 matrix, which is obtained by reversing the order of the column of the identity matrix I6. Let P. Okay, we have defined the matrix P is where alpha, okay, here alpha is a non-negative real number, the value of alpha for which the determinant of this P matrix will be 0. Okay, so we have to find the value of alpha. So first of all, let form this matrix P. So here we can write, here we have to write I6 matrix, identity matrix of the sixth order. So here 1 0 0. Okay, so let's write whole matrix. Okay, here 1. Let's plus add this alpha times j6. Okay, let's write this j6 matrix here as it is. Okay, now let's do the addition of this both matrix here. So what do we get? Okay, in the first row we have 1 from this identity matrix. Okay, now the remaining all these 4 entries remain 0 because here we have 0, here 0, here 0, again 0, 0. Okay, so in the last entry we get the alpha from this second matrix, so we can write alpha. Now the same manner in the second row we have here first element is in 0, second is 1, again we have 2 0 and alpha from this second matrix in 0. Now in the third row we have here 1, here alpha, again 0 0. In the fourth column, so in fourth row we have alpha 1. Now in the fifth one we have like that. Now in the last row we have alpha here. Now again we have 4 times 0 and in the last we have 1. Now they are asking about the determinant of this matrix P. We have this matrix is equal to 0. Okay, so we have to find the value of alpha such that the determinant of this whole matrix, which is an 6 cross 6, will be 0. So now what we are going to do is that we know if the any two rows of the any matrix are similar or linearly dependent, then we say the matrix determinant of this matrix is 0. It does not matter the size of the matrix, even it is 100 cross 100 matrix. Then we can say also if the any two rows are similar or linearly dependent, then the determinant of whole matrix will be 0. So here we can see from the this two row number 3 and 4, if we have to make this two as a same, so we have to select the alpha such that here the entry and here the entry will be same. So now you can see directly that if alpha is equal to 1, then r2, sorry, r3 will be exactly same as r4. In the similar manner you can see r2 and r R4, R5, sorry, will also similar. In the same way, R1 and R6 are also same, but at least if any two rows are similar, now at least two rows are same or linearly dependent, then we can say the determinant of whole matrix is 0. So here the alpha value of alpha is 1, such that the determinant of this whole matrix will be 0. Okay. Okay. Now let's solve question number 2. Question number 2 says the system of linear equation. We have given three simultaneous equations. They are asking about the solution of this system. We have to find the solution of this system. So first of all, let's form augmented matrix from this given data. So we can write here 2, 1, 3. Here we have 5. Here 3, 0, 1. Here we have minus 4. Okay, here we have 1, 2, 5, and here 14. So let's apply some row operation on this matrix such that we can reduce it into echelon form. So let's R1 minus 2R3 will be our new R1, and R2 minus 3R3 will be our new R2. Uh, After these two operation, what we are getting is, okay, we have 2 here, and minus 2 comes from this third row. So here we get a 0. Now here we have 1, and here we get minus 4. So we have minus 3. Now in this third element we have minus 10 here, plus 3. So we get minus 7. Now here we have uh, minus 28 from this third row, and here we have plus 5. So we get minus 23. Now in the second row we have 3, and we have minus 3 from this third row. So here we again get 0. Now here we have minus 6 because we have multiply with minus 3 in the third row and adding in the second row. And here what we are getting is minus 14. Now here we have minus 4 and 14 multiply with minus 3, which is minus 42, and minus 4 minus 46. Okay. Now here we have third row is remain as it is, 1, 2, 5, and 14. Now let's do some further operation to reduce it. Now we can see if we multiply with 2 in the first row and add it into the second row, uh, we get all rows in 0 because they are linearly independent. Sorry, linearly dependent. So let's do what we are going to do is just R2 minus 2 R1 becomes our new R2. So R1 is remain as it is. Here we have minus 23. Now in the second row we have 0 already the first element. Now here we have plus minus 6. Now here what we are getting is plus 6 because we are multiplying with minus 2 and adding. So here again we get 0. Now in the same manner we again get 0, and here we also get 0. The third row is remain as it is, 1, 2, 5, and 14. Now you can see, you can, if you want, then you can rearrange this matrix like this. Let 1, 2, 5, here 14, 0, minus 3, minus 7, minus 23, and 0, 0, 0, 0. Now you can compare the rank of this A matrix. This matrix is equal to rank of A augmented B. This whole matrix are both equal and equal to 2. Now you can see if you find out the value of uh, uh, this C variable from here. So what you find is in the third row that C will be independent, and you can uh, assume it any variable, any value in the uh, real number. So uh, from that you can get value of A and B in terms of this t, and t is an arbitrary value. T belongs to R. So you can select any value and you are getting ABC. So you get the solution according to your uh, chosen T value. So we can say the system has infinite solution. You can also say it from here because 2 which is less than 3, which is 3 is number of unknown. We have 3 unknown here ABC, and the rank of this augmented matrix in a reduced matrix is 2. So there is a 1 deficiency of the rank. So you can also say the nullity of this matrix is 1. So there is a 1 independent solution. So the system has infinite number of solutions. So option C is the correct choice. Now let's solve question number 3. Question 3 says, given the matrix, okay, we have given a J 3 cross 3 matrix and I, which is column matrix 3 cross 1, and they are asking about the product of K transpose multiplied by J multiplied by K. So let's first find these two. So we can say K transpose times J. So first of all, let take the transpose of this matrix. So what we are getting is just simply 1, 2, minus 1, which is an 1 cross 3 row matrix, and J is remain as it is 3, 2, 1, here 2, 4, 2, and here 1, 2, 6. So here we have 3 cross 3 matrix. Now you can see in the output we are getting uh, 1 cross 3, again the column matrix, 1, sorry, row, simple row. So let's do the multiplication. Here in the first element what we are getting is just simply 3 plus 4 minus 1, which is simply just 6. Now in the second element we are getting 2 plus 8 minus 2, 8. In the third element we are getting here 2 plus 4, which is 5, and minus 6 minus 1. So okay, so we have find out this term K transpose multiplied with J, and now we have to multiply this answer to this column matrix. So let's do it. We have to multiply it with K. So let's first write this matrix 6, 8, minus 1, and write this column matrix. Now you can see which is 3 cross 1, and here it is 1 cross 3. Now in the output after multiplication you get only one element, which is 1 cross 1. So let's do the multiplication and solve it. So what we get here is 6 plus 16, 8 multiplied with 2, and here minus minus become plus 1. So from here you get 23. So here you get 23. So here your answer is 23. Okay. Okay, let's solve question number 4. Question 4 says the sum of the eigenvalue of the matrix. Okay, we have given a matrix M. They are asking about the sum of the eigenvalue. Now here you can see uh, the entries in the matrix which are very large in the number. So we do not have to find the values of lambda 1, lambda 2, and lambda 3 for this matrix. To find out its sums, we just simply use properties of eigenvalues, and we are going to use the sum of the all eigenvalues of this matrix, because it is here 3 cross 3 matrix, which is equal to trace of this matrix M. So let's find the trace of this matrix. Now the trace is nothing but the sum of these three diagonal elements. So let's do it. 215 plus 150 plus 550. So here 215. So you can add this both value. You get 700. Now if we get 915. So option B is the correct one for the sum of all eigenvalues. Okay, let's solve question number 5. Question number 5 says the determinant of the matrix. Okay, we have matrix which is 4 cross 4, and they are asking about the determinant of this matrix. So first of all, let's reduce this matrix so that we can easily find its determinants, because it is a 4 cross 4. So we have to first decompose it into the minor of 3 cross 3, and then we can find the determinant. So first of all, we are trying to reduce this matrix, and then we are decompose it into 3 cross 3 minors, and then we find the determinant. So first, like some operation, row operation. Let's do R3 minus R2 becomes our new R3, and R4 minus 3 R2 becomes our new R4. Now let's apply this both operation. The first row is remain as it is. Now in the second row is also remain as it is, because we are applying the operation on the third row and fourth row. So here we get 2 minus 2, here we get 0. Here again 3 as it is. Here we get minus 6 because no, sorry, we will multiply with minus 2. So here we get minus. So here we get minus 6, and here 1 as it is. Now in the third row we have 3 here. Minus 3 comes for the second row. Again first element is 0, second is also 0. The third we have uh, minus 9 from here and 1 here, so minus 8. In the last element we have 2 as it is. Okay, now it is easier. You can see that the first column is reduced in the form. It has 3 0 and only one entry as in 1. So now you can decompose it about any rows and column, but I am doing about this first column because you can see that it has only this element, one element, and I have to write the corresponding minors of this element only, because all the other minors of corresponding the corresponding minors of this 0 and this 0 does not effect over the our determinant value of this matrix. So let's decompose it about this column, first column. So here we have 1 as it is. We have to neglect this row, and this column is contain this element. So we have to write the 3 cross 3 matrix remain as it is, which is left after deleting this row and column. So let's write here 0 minus 8 and 2, but now here we have to multiply it with the sign factor, which is minus 1 raised to I plus j, and I is the I and j is the index of this element, which is corresponding to a to 1. So here we get minus 1 raised to 3, because we have to add up these two values. So in the output we get minus here, and now let's find the determinant of this 3 cross 3 matrix. So here 1 as it is, we have minus 12, sorry, we have minus 12 plus 8 minus 2, and here we have 6 minus 0 plus 3 multiplied by minus 24. Let's simplify a little bit. So you get minus 4 here from the first term, here it is 0. From the second term you get minus 12, and from the last term 24 multiplied with 3 you get 72, and minus remain as it is, so 72. Now if we add up all three values, we get, what we are getting is minus 28, sorry 88, and here we have minus and we have outside minus also, so which become positive 88. So the determinant of this matrix is 88. Okay, let's solve question number 6. Question 6 says if the following statement, which of the following statement is true about the every n cross n matrix with only real eigenvalues. Okay, we have given matrix which is the dimension of n cross n dimension, and so we have n eigenvalue corresponding to this matrix. So and all are the real. So first let's check option A. What option A is saying that if the trace of the matrix is positive, okay, we know the trace is the nothing but the sum of the all eigenvalues. So let's assume this matrix is n eigenvalue. So lambda 2 plus lambda 3 plus up to lambda n. Now this sum equal to the trace of the matrix by the property of the eigenvalues. We can say it is a positive from this statement positive, and the determinant of the matrix is negative. Now we have also know that the determinant of any matrix which is nothing but the multiplication of all the eigenvalues of this matrix. So here we have n eigenvalue, and it is given in the statement that determinant is also negative, not positive. Okay, determinant also is negative, and they are saying that at least one of its eigenvalue is negative. Okay, uh, so the determinant is negative, which means multiplication of this n value, we are getting the negative number. So we can conclude that at least one of this n value must be negative. Maybe it is possible that more than one value, either one value or three value or five in the whole term. If the values are negative in the odd manner, either three values are negative or one values of this eigen value is negative, then output in the multiplication we get the negative number. Now in the addition, if uh, suppose this only is the negative value on the lambda, and the other sum of the other eigenvalue which is greater than this number, then in the output sum will be positive. So option A looks like correct. First of all, let's see other option also. So option B says if the trace of the matrix is positive, okay, we have given again the same condition. The sum of this n value will be positive, and the other condition is the trace of the matrix is positive, and they are saying the all its eigenvalue are positive. Now it is not necessary. Suppose let lambda 2 and lambda 3 is negative. So now if the sum of the remaining n minus two values of this lambda is greater than this sum of these two, then in the output we get sum is a positive number. So but the still two, but the values of these two eigenvalues are negative, and the statement says all its eigenvalue must be positive. So option B is the wrong statement about the eigenvalues. And now option C state that if the determinant of the matrix is positive, okay, the same condition here which is given, the multiplication of all the eigenvalues which is positive, and they are saying that all its eigenvalue are positive. Okay, now again it is not necessary that the all eigenvalues are positive. Suppose any two, let's suppose lambda 1 and lambda 2 are negative. Now in the output you still get the positive number because we have two values are negative, they are multiplied with together, and we get the plus number in the multiplication. So again statement C is the not correct one always. So let's check option D. If the product of the trace in the determinant of the matrix is positive, then all its eigenvalue are positive. Okay, so they are saying that if the trace that means if the sum of this all n value multiplied with the multiplication of all this n value, now it will be positive number, then they are saying that all its eigenvalue must be positive. Now again this is not always the case. Suppose if let's assume lambda 1 and lambda 2 are negative, so here these both term are negative, so after multiplication we get a positive number from here. Now here again the same thing, if the sum of this other eigenvalue excluding this lambda 1 and lambda 2 are higher than the is higher than this both value, then we can again we again get the positive number from here. have to multiply this number with this number, and then in output we always get the positive answer. So option D is the also not always true. So the remaining option is the C, which is the must be true, such that to satisfy this condition. So option A is the correct choice. Okay, let's solve question number 7. Question 7 says the rank of the matrix. Okay, we have given here a 3 cross 4 matrix, and they are asking about the rank of this matrix. So first of all, let's reduce it into echelon form by some row operation. So here, first of all, let's write as it is 0, 4, 4, minus 2, 14, 8, 18, 14, minus 14, 0, minus 10. Now, what we are going to do is just simply, okay, if we multiply this first row by 2 and subtract from third row, so what are we getting? Let's say R3 minus 2R1 becomes our new R3. So let's do this operation. So in the output, the first row is remain as it is, second is also remain as it is, because we are applying the operation only on the third row. Here 18. So let's here 14, and here minus 12 come from the first row. So here we get in the output as plus 2. Now in the second element, here is 0, so minus 14 remain as it is. Now here in the third element, we have here minus 8, because we have multiplied with minus 2, and here already is 0, so minus 8. Now in the last element, we have minus 8 from the first row and minus 10 already, so we get minus 18. So now you can see that uh, row 3 and row 2 are linearly dependent. So let's do further one operation to reduce it. So let R3 plus R2 becomes our new R3. Simply add this second row into the third row. So first is remain as it is. Second is also remain as it is. In the third row, we have here 0 as an output. Also here 0. Also 0 here. The fourth one is also 0. So you can see that now you can reduce further this two row by some other operation, but it is not necessary here to reduce it, because we are interested in finding the rank of this matrix. You cannot make any row this remaining two row as a perfect 0, like we did in the with this third row. So you can say that the number of non-zero rows or linearly independent rows of this matrix is 2. So the rank of this matrix will be 2. So the correct answer is 2. Now let's solve question number 8. Question 8 says, with reference to the conventional Cartesian XY coordinate system, the vertices of a triangle have the following coordinates. Okay, we have given three coordinates of the vertices of a triangle, and they are asking about the area of this triangle, which is formed by these three vertices. So first of all, let's write it. We have given x1 y1 is in 1 comma 0. We have x2 y2 is in 2 comma 2, and x3 y3 4 comma 3. So let's suppose that let us assume our this x2 x1 y1 point is here in our Cartesian coordinates, and let's suppose this is our x2 y2 point in the Cartesian plane. Now here, and we have x3 y3 point is here. So now we are interested in finding the vector that join this both point and this both points. So let's draw the arrow to denote the vector. Okay, so this is vector which is connect this x1 y1 vertices with this x2 y2 vertices, and let's here again the other vector which is connected with this x1 y1 and x3 y3. Let's call this vertices is a, this is b, and this is c. Okay, now let's find this ab vector and this ac vector. So ab vector, now how we can find it? By simply just subtracting this a's coordinate from the b's coordinates. So let's subtract. We have x2 y2 here is 2 comma 2, and a's coordinate is x1 y1 which is 1 comma 0. Now do the subtraction. So what we get is just simply 1 comma 0, because here we have to subtract minus 1 from this x1 coordinate, and here we have to subtract 0. So 2 remain as it is. And now this ac vector and vector AC is found in the similar manner. Coordinate of this C point minus coordinate of this A point. So here coordinate of this C point is 3 comma 0, and A point is 1 comma 0. So you can get 3 comma 3. It is an vector which is connect with A and C, connected in A and C. So now uh, we know that the cross product of any two vectors. Let's vector A cross product with B. It is just simply give the area of this, which is uh, formed by this two matrix parallelogram, which is formed by these two matrix. So here, if suppose I translate this vector parallel to this vector up to point B, and I redraw it here. So what I am getting is like that. Okay, which is parallel to this matrix, and if I translate this AB vector parallel to it up to this C point, and I redraw it here. So here what I am getting is just simply a parallelogram, and if I am interested in the finding the area of this parallelogram, then I just simply do the cross product of this AB vector with this AC vector, and I find the this area all. Now but here in the question they are asking about the area of the triangle. Okay, so they are asking about the area of this triangle which is formed by these three vertices ABC. So what we are just simply going to do is just first of all find this uh, cross product of these two vector, and just take the magnitude of it and divide by 2, so that we get the this area, half area, because we are interested in finding the area of triangle. So here and the vector product, here the cross product is a vector, so we have to take its magnitude. So first of all, let's find this cross product AB cross AC. Now how to do it? It is just write here I cap, here j cap, and the unit vector in the x, y, and z direction, and just write the coordinate of this AB vector here and AC vector here 3, 3, 0. Now solve, and so find its determinant. So we get I here, the unit vector in the x direction, and here, and we get 0 minus unit vector of y direction, and we have to find its corresponding uh, cofactor. So here again 0. Now plus k vector, and we have to find this 3 minus 6. So we have find out is just minus 3 k cap. It is indicating in the z direction, but we have to find its magnitude. So we can say the magnitude of vector AB cross AC is just simply 3. So we are interested in, here we are interested in the area of this triangle. So let's divide this 2 by 3 by 2. So what we get, the area of triangle, which is nothing but 3 by 2. So option A is the correct choice for the area of triangle which is formed by these three vertices. Now let's solve last problem, question number 8. Question number 9. Question 9 says the maximum value of the determinant among all the 2 cross 2 real symmetric matrices with the trace 14. Okay, so they are asking the maximum value of determinant that could be possible for the whole 2 cross 2 real symmetric matrix such that the trace of the matrix is 14. So okay, we have given the condition the trace is 14, which is nothing but the sum of the eigenvalues. We know from the property of eigenvalue, and here the matrix itself is 2 cross 2, so we have two eigenvalue. Let's assume it's lambda 1 and lambda 2. So we have lambda 1 plus lambda 2, which is given as 14 is the trace. And now they are asking about the maximum value of determinant, which is nothing but the multiplication of these both eigenvalues. So now we can find the values of lambda 2 here in the term of lambda 1, which is 14 minus lambda 1. And now we just simply put this value here for lambda 2 in this determinant equation. So we get determinant is equal to lambda 1 remain as it is. Now the lambda 2 is replaced by 14 minus lambda 1. Now let's do the some multiplication with both of these. So we get 14 lambda 1 minus lambda 1 square. Now we have to find the maximum value of this determinant here. So what we are going to do is just simply take the first derivative of this function and equate is equal to 0. So let's del d by del lambda 1, because here lambda 1 is our variable. So here after the derivation we get 14 2 lambda 1. Now equate del d by del lambda 1 equal to 0, because we are finding the stationary point of this function. Okay, so let's equate is equal to 0. So here 14 minus 2 lambda 1 equal to 0. From there you can get lambda 1 equal to 7. Now to make sure that this stationary point is corresponding to the maximum value, so uh, for checking that we have to take the second derivative of this determinant. So let's do the second derivative del square lambda 1. So let's differentiate again it with respect to lambda 1. So here output we get minus 2, which is negative, and we know if the second derivative of any function is negative, then it is a maximum. So we can say that at the lambda equal to 7, this function, which is represented by 1741 minus 40 minus lambda square, will be maximum. So here we can find the value of maximum determinant. We can also find the corresponding value of lambda 2 from the here, because we have given the sum is 14. So you can also conclude that lambda 2 is also 7. And now you can find the maximum determinant of this matrix that could be possible with trace is 14, which is nothing but 7 multiplied with 7, which is minus 49. Okay, so the maximum determinant of all the 2 cross 2 real symmetric matrix with trace equal to 14, it is the minus 49. Okay, so that's it. Thank you for watching.